Thank you so much, everyone, for joining, identifying, and avoiding malicious packages. We're really excited to have you here. We have a lot of great content to present to you, and I'd love to introduce you to our Director of Threat Research at JFrog Security, Jonathan Sar Shalom.
Thank you, Rebecca. Hello, everyone. My name is Jonathan, and I'm the Director of Threat Research at JFrog Security. Our topic for today is identifying and avoiding malicious packages. We're going to learn the technical details about the world of malicious packages, as well as how to identify and prevent an infection by one. So a few words about myself. My background includes more than 13 years in cybersecurity with experience in security research, reverse engineering, and malware analysis. Nowadays, I'm leading the threat research team in JFrog Security, specializing in vulnerabilities analysis, threat intelligence research, and automated threat detection. As for the agenda, we will first introduce the security threat inherent in supply chain and learn the key role that malicious packages play in it. Then we will dive into the technical details of malicious packages infection methods, common payloads used in malicious packages, and how attackers hide the malicious code in them. Often we will take a look on real code examples of malicious packages when the majority of the examples that we will present are real malicious packages that were found by JFrog security researchers and were publicly disclosed. Finally, we will present techniques to detect and prevent malicious packages, both known and unknown, and show the best practices for secure code development to avoid and mitigate the risk of malicious packages. So when we talk about the malicious packages security threat, we first need to understand the bigger problem that the malicious packages are a part of. This is the supply chain attacks. In modern software development, many applications integrate third-party software in their code and trust the third-party software to supply a secure and stable software. In reality, this practice also involves some danger, of course, because third-party software might contain vulnerabilities or malicious code that will be delivered through the supply chain of third-party software together with the software itself. These vulnerabilities and malicious code will eventually affect the end products and the end product that depends on it. Essentially, software supply chain attack is a technique in which an adversary slips malicious code or an entire malicious component into a trusted piece of software or hardware also. So from a technical point of view, if you look at the term here in this slide and the essence of this, you will see that there are no single targets that are being involved in this attack, because when you attack a supply chain by infecting a software package, for example, you will eventually end up with attacking all of the end consumers of this supply chain. So you can understand already the first reason of why an attacker would go for the supply chain approach, because of the high distribution of the attack. Let's talk now on the effort that the attacker needs to invest in a supply chain attack compared to classic targeted attack that we've seen a lot in the last 20 or 30 years. And it will help you understand why this attack method became so popular recently. In a classic targeted attack, attackers has to invest a lot of time and money for compromising a single target. And it becomes even harder when the target is a known software platform, because those platforms are highly maintained and secured compared to many relatively small software packages that are out there. So for a targeted attack, an attacker would need high technical skills, because it essentially involves finding a vulnerability and developing a working exploit for it. You can take a look at the pricing table here on the right, taken from Zerodium, which is an exploit acquisition platform, actually. You can see that a remote code execution exploit can cost up to $1 million for a single exploit, when the most expensive one is a zero-day RCE, a remote code execution exploit for Windows. When attacking a malicious open source software, for example, the options are endless. There are many packages out there, so the attackers simply have to find a single package to attack, or to publish a single malicious software package, and it's a game over for the entire consumers of the supply chain of this package. So as we said, this essentially abuses the trust that exists between parties in the supply chain, making this attack method so effective. There are three different types of supply chain threats. Two of them are based on software vulnerabilities, whether intentional or unintentional ones. Those vulnerabilities usually refer to software bugs, where each bug is normally assigned with a CVE identifier. CVE is a common standard to describe vulnerabilities and exposures, and they are widely used to document and track vulnerabilities in software. The third type here in the right side of the slide is the third type of the supply chain threat, and this is the one that we're going to focus on today, is the malicious component or the malicious software package. Usually, CVE is not assigned to this type of threat, and the entire package or specific version of the package simply tagged as malicious. Let's see a few real-life examples for each. So for the unintentional bug, we have, of course, the infamous log4shell vulnerability that shook the world a few months ago. The log4j package is highly used by Java projects, so the global effect of this vulnerability was really huge. For the intentional bug, we can see also the famous SolarWinds attack, when SolarWinds Orion software platform was attacked and a backdoor was injected to it. Thousands of consumers of this software were affected by the attack, leading to even more follow-up attacks that were carried out later. So in this presentation, of course, we're going to focus on the malicious components threat. And here we can see an example from one of our publications on malicious Python packages specifically that we found and disclosed recently. So after introducing the supply chain attacks and how malicious software packages play a key role in it, let's dive into the technical details. First, we'll start with the infection methods attackers use for spreading malicious packages. There are several main infection methods that we will present. This includes the Typosquatting infection method, the Masquerading method, Trojan packages also, dependency confusion or name squatting, and also packages hijacking. The first infection method is called Typosquatting. Typosquatting is the practice of obtaining or squatting a popular name with a slight typographical error. This practice applies to many different resources, such as web pages, executable names, and also software packages names that we're going to focus on today. Let's take one classic example, buying the domain name google.com instead of the legitimate known google.com, hoping that users will occasionally make typing errors and reach the illegitimate domain. This can further be used for any kind of attack payload, such as phishing and code injection attacks. We actually, in a trend that we're seeing recently, some maintainers and developers of software packages take an active role and actually reserve Typosquatting prone names for their projects. This is for preventing attackers from taking control of them. Regarding our example of google.com, Google actually registered this domain specifically. So if you browse to google.com, you will end up be referred to google.com. Here you can see the first example that we will see today of a malicious package that used the Typosquatting infection method. This package was detected in a recent research conducted by our researchers in JFrog security by using automated heuristic scanners that detect malicious activity in open source packages. We will elaborate on the heuristic detection of malicious package later, but for this case specifically, the scanners found that the software package contains a payload with a crypto miner activity. As for the specific typosquatting attack that was used here, the malicious package name mplatlib, which you can see here in the console, is very similar to the legit package mplotlab, which you can see here in the npm side. As you can see at the console log, at the time of research, the malicious package could be installed by a simple typo error. Of course, the existence of this package, as well as other malicious packages, were reported to PyPI and was removed since then. Beside typo squatting, there is an interesting trend of another infection method in which malware authors completely duplicate a well-known package. The authors or the attackers duplicate both the code and the metadata of the original project, which they would like to impersonate. And then also add a small piece of malicious code to this duplicate, essentially building Trojan package. This infection method is similar to the typosquatting infection method in a way that the attackers use a name similar to the legitimate package name, but the difference is that they aim to deceive developers through a similarity to the legitimate package rather than aiming for accidental use due to typo errors. This is an example that you can see here of the malicious package mark.js, which was found during one of our latest researches from last month, actually. You can see that the original name and metadata of the mark.js malicious package were copied from the original legit marked package, making it very hard to distinguish between the two. The URL of the repo is the same, as well as the homepage and the description and the entire metadata. The only thing that is different here is actually the package name, which is mark.js instead of marked. And this can also confuse a lot of developers that will go and install the mark.js package. When comparing the malicious package marked.js code with the original package marked code, we can see that the only difference from the original package is one line in a single file. This is the long line here marked in black. You can see that this line does not contain a readable code, and it relies between other legitimate and readable lines. This is actually the obfuscated malicious code, which is the only addition to the original legitimate package, making this modified package to be a fully functional from one side, but also malicious from the other side. We will talk later about the obfuscation techniques and the different payloads that are often used by attackers. But one thing to remember for now is that since this line is buried inside the rest of the package, which contains a lot of legitimate code, it would be very difficult to find this line without automated scanning or diffing tools. Another infection technique is a Trojan package. In this infection method, the attacker publishes a fully functional library, but also hide a malicious code in it. The same as the masquerading method, the malicious code is usually small and obfuscated. Therefore, it is hard to detect and differentiate between it and the legitimate functionality of the package. In the screenshot here, you can see an example of the README file of a very interesting Trojan package called Lemma. This malicious Trojan package was caught by our scanners in one of our latest published researches. This package is a utility for Discord accounts hacking, intended for use by malware authors to hack Discord accounts. So first of all, a short break to explain about the Discord network for those of you who are not familiar with it. Discord is a communication app with hundreds of millions of registered users that allow voice calls, video calls, text messaging, and so. The identity of a user in the Discord network is presented in a string called the Discord token. which is basically a set of letters and numbers that acts as simply as an authorization code to access the Discord servers. It's effectively a user's credentials that can give the attacker full access to the victim's Discord account. So going back to our Lemma library here, as we said, the library itself is a fully functional published library, which is actually meant to be used by attackers to steal Discord tokens. So the interesting story here is that the Trojan code in this package is aimed to steal the Discord tokens from any attacker that uses this library for token stealing. When the library is used, it will hijack the secret Discord token given to it, in addition to performing the requested utility function. So take a look on the malicious code of this library. Here in the obfuscated code, you can see this function that contains a payload that hijacks the supplied Discord token and send it to a hard-coded web URL, which you can see here, essentially sending the token to the attacker control side. In the deobfuscated code here at the bottom, we can confirm that the function name is remove all friends, and we can see it uses HTTP post request to send the supplied token. You can see it here. Regarding the obfuscation, since the function is in malware library itself, in the malware library itself, it's actually not overly suspicious that its code is obfuscated, and thus novice malware authors may trust this module even with its obfuscation. The next infection method called dependency confusion. And it exploits a vulnerability in the way that many package managers download dependencies during a build process, for example, pip or npm. The vulnerability resides in the fact that most package managers, such as pip and npm, do not distinguish between internal packages hosted on internal company servers and external ones hosted on public servers. Thus, simple commands such as pip install my package would grab my package either from an internal or public server. In the dependency confusion method, the attacker uses a specific package name of internal package of a specific target and publish a malicious package on an external public repository with this exact name. Usually the attacker also assign a very high version number to this published package. In this scenario, most of the default package managers, as we said, will prefer to download the external malicious package because it has a high version number rather than downloading a low version number from the legitimate internal repository. We can see here in this screenshot a nice example from a research that was published last year by a security researcher named Alex Birsan. What we can see here in this screenshot is a publicly available package in PyPI with a name that looks like an internal package of Netflix. You can see the NTFLX here. And a very high version number, which is 6969, which is very high. With this attack, Birsan managed to successfully exploit Netflix as well as Apple, Microsoft, and other giants by making their servers to download the malicious external package instead of the legitimate internal one. Another example of dependency confusion attack can be found actually in a research that we in JFrog Security published in last December. As you can see in the list of malicious packages that we detected as part of the research, among many packages that use the Typosquatting attack method, we can see one package that was probably spread using a dependency confusion attack. It can be easily detected with a ridiculously very high version number that generally not used in normal product versioning. You can see it here. The last infection method that we will talk about is the package hijacking. This method involves taking over a legitimate known package and pushing a malicious code into it. While this is not an easy task, it is very effective because it can take advantage of the popularity of very known packages for a high infection rate. The hijacking is usually performed by hacking maintainers' account and developers' account, or by injecting hidden or obfuscated malicious code as part of a seemingly legitimate code contribution to an open source project. Several months ago, it was detected that a few notable legitimate packages were attacked and hijacked by taking over the maintainers' accounts and pushing malicious code to several versions of those packages. In this screenshot, you can see one of the packages, one of the hijacked packages called UA parser.js. This is a very popular package with almost 1 billion downloads to date. The interesting thing in this package is that the malicious code that was injected to this package was the same as in another malicious package that originally masqueraded this UA parser.js package. We can see here the announcement by the developer of the package saying that he believes someone hijacked his package and published a malicious version of it. This incident and other recent incident made GitHub to actually enforce two-factor authentication for maintainers and admins of popular NPM packages. By the way, it is also worth mentioning the publicized incident of the known NPM packages Faker and Colors, where their maintainer intentionally sabotaged these popular packages, adding some sort of infinite loop into their code, which bricked thousands of projects that depend on them. You can say pretty much that he hijacked his own project and created a lot of damage by doing that. So now that we presented the infection methods that are used by malicious packages, we can continue to the payload phase. After a successful attack or infection of a malicious packages, usually the attacker would like to execute a payload that will serve his needs. So we will present some very common payloads that are executed in malicious packages. We will mention and analyze sensitive data stealers that exploited user data, also connectback shells, download and execute payloads, and of course, the very popular very popular payload of crypto miners. The first payload that we take a look at is a sensitive data stealer, which steals credit card information from the autocomplete feature that we have in modern web browsers. Essentially, for autocomplete to work, modern browsers save in their databases previously typed user information, such as addresses, passwords, and credit cards information. This is very convenient for the user, but the downside is that this information can be leaked by malicious actors that get access to the local machine. In the code snippet here, we can see the payload code of a malicious package called Noblesse, which we found in one of our research projects last year. We can see that the malware tries to steal credit card information from Chrome browser by connecting to its internal database. You can see the connection string here, and the querying for credit card information, and you can see it with this SQL query here. Essentially, the package sent this information to the attacker. So this is very dangerous practice. Additionally, the same malicious package that we just seen also tries to still save the passwords. In this case, specifically from Edge browser database, you can see the path of the saved passwords that the malicious code connect to it, and then the SQL query for querying those passwords. Another interesting data stealer is a Discord token stealing payload. This payload simply tries to steal a user's Discord token, which we already mentioned earlier. In this payload, the stolen Discord tokens can be used to log into the victim's Discord account. So So the account can be used, for example, as a proxy in another future attack, or be used to spread malware to other Discord users that trust this hacked account, or when the attacker is lucky enough to come across a premium account, they can sell it and actually make profit from it, of course. It's also very interesting for a payload to steal information in environment variables. So this is another data stealer payload, the environment variable payload. In a research, in a research we conducted in last December, we disclosed 10 malicious packages that performed environment variable theft. Those packages were spread by a Typosquatting attack, and it was noticeable that they do not contain any legitimate functionality, but rather contain a small snippet of malicious code, which is possible to understand even when obfuscated, as we can see here in the code snippet. In the code snippet, you can see that the malware gathers all of the victim process environment variables and posts them to a remote URL, which you can see the post request here. This is a dangerous payload, since environment variables are a prime location for keeping secrets that need to be used usually by runtime software. This is a common practice in production system because saving secrets in runtime is safer than keeping secrets in clear text storage or passing the secrets via command line variables, for example. So here you can see an example for this data. Specifically the AWS command line interface, which supports getting the AWS secret access key from an environment variable. And this is a very common practice for AWS deployments, as can be seen in the above configuration example. The next payload type is the Connectback shell. The purpose of this payload type is simply to receive remote commands for execution on the victim's machine. So generally in this payload, there are simple 3 steps. The first one is connecting back to the attacker's server, then receiving commands to execute, and then sending back the execution results to the server. So let's take a look at an example from another malicious package we found and disclosed in JFrog security. Actually, very recently in last month. These are 2 Trojan packages named HPAD and HIPAD, which are Python libraries that supposedly meant for hiding processes in Linux through the API that they provide called hide processes. In reality, when this API is called, it also calls the function release elf that you can see here, which install a command, a Connectback shell that is aimed exclusively at Linux target machine. Let's take a look on this release elf malicious function. We can see that it decodes a base 32 Trojan binary. You can see it. You can see it here. It is interesting that this Trojan binary is embedded in the Python code as base 32 string, because it is an uncommon encoding comparing to base 64 that is widely used. This base 32 encoding may have been used for evading automated scanners, which do not expect this kind of encoding. So after the decoding, the Trojan package is written to the path of syslogd binary, which you can see here, simply for replacing it. Also, you can see that the owner permissions and the timestamp are copied to this new file from another system file to make the Trojan file similar to other system files and avoid detection. You can see it here with the chon, chmod, and the touch commands. In the last line, the Trojan file is executed using the function popen. Next, the drop Trojan is being executed, and this is actually an elf file that is quite small and obfuscated. When executed, it performs the 3 steps of a classic Connectback shell that we already described. Connecting back to the attacker server, receiving commands to execute. You can see it here, the popen that received the commands, and then sending back the execution result to the server by encrypting it and sending it to the attacker server. The last payload we will talk about is the crypto miner payload. This payload utilizes the victim's system resources for the mining of cryptocurrency. We're not going to dive into the technical details of crypto mining due to time constraints, but keep in mind that this is a very common payload type in malicious packages, simply because of the nature of malicious packages attacks. As you remember, most of the time, malicious packages are not used in a targeted attack, but rather by spreading them to as many victims as possible with all of the infection methods that we mentioned earlier. So utilizing many system resources from many victims is a good idea for a profitable payload such as the cryptocurrency miner. In these code snippets, you can see that the payload of Maratalib package, this is another malicious package that we recently detected that was spread using the Typosquatting attack. In the above code snippet, you can see that as part of the setup code of this package, it also downloads and executes a remote bash script called aza.sh that you can see here. In the screenshot below, we can see the code of this bash script, which also downloads and executes a known crypto miner called Phoenix miner that you can see here. This is actually the actual payload, the actual crypto miner, which sends also after that to the wallet of the attacker, which you can see it here. This is a cryptocurrency malware for the cryptocurrency called Ubiq. So now that we talked about the infection method and the payloads that are usually used in malicious packages attacked, we will talk about another main interest that the attackers have when creating a malicious package, which is hiding the malicious code. So besides performing a successful infection and payload execution, malicious packages authors would want to avoid the detection of their malicious activity. For achieving a good success rate of an attack, attackers would like to avoid detection by code analysis security tools, and also to make it hard for any security researcher to reverse engineer their malicious package. So this is a very common technique for achieving these goals, and it's called code obfuscation. We're going to discuss several code obfuscation techniques, including off-the-shelf public obfuscators, custom obfuscation techniques, and also an obfuscation method, which is an invisible backdoor, which is not an obfuscated method by itself, but rather a technique to invisibly change the source code logic without producing any visual artifacts. So let's take a look on a public obfuscator, for example. This obfuscator is simply called Python obfuscator tool. It was used in Nobles 2 malicious packages we found last year. The obfuscation mechanism here is simply the encoding of Python code text with base 64, and then decode it on runtime, compile it, and execute it. This is a very simple technique. In the code snippet, we can see an example of a hello world print in Python that was obfuscated automatically with this tool. We can see the usage of base 64 strings here, the decoding of them using the B64 decode function, and also the compile and eval functions that are called to execute the decode code. This obfuscation can trick a simple static analysis tool, but doesn't stand against more thorough analysis, and actually raises a red flag that will make many security researchers to take a closer look at this code, and that was actually the case with this example when our automatic malicious packages detection scanners alerted this kind of behavior. Let's take a look at another obfuscation technique, a more complex one called the control flow flattening. In this technique, the structure of the code's control flow is broken into blocks that are put next to each other instead of their original nested levels. This method was used in a malicious package we detected called disclosed. The package payload was a Discord token grabber, and it was spread by the Typosquatting and the Trojan infection methods. We can take a look on this technique with an example from a paper that was published on this subject. Look at the original code on the left side here. We can split it to three code blocks. First, we have the variables initialization at the top, then a while loop with a break condition, and finally the code block inside the while loop. On the right side, you can see the code after applying the obfuscation with this obfuscation technique. You can see that the three code blocks are flattened, and a switch case is used to control the flow of the code. You can see the switch case here. You can also see that the variable SWVAR here holds the number, the ID of the code block that is being executed right now. And in the end of each code block, its value is changed to indicate the next code block that should run. So basically, with this switch case, when the code run, it will call the next block that should run, even in a dynamic way. So you can see here, when we take a look on the while loop, you can see that we can end up in code block number 3 or in code block number 0, which is the end of the program. And this of course implements the while loop, the while loop here that we can see in the left side. Lastly, we will talk about a technique called homoglyph characters attacks, which is not an obfuscator by itself, but it can be used to hide malicious code modifications in legitimate software packages. This technique was published in the recent Trojan source paper, demonstrate the possibility of changing source code in an invisible way. It essentially means that the logic of the code can be changed to contain a vulnerability, for example, without producing any visual artifacts. In this technique, attackers use Unicode characters that look like standard ASCII Latin characters that a normal reader wouldn't notice. But the compiler or the interpreter will treat them differently, so the logic of the code will be changed. This technique can be used by supply chain attackers to plant invisible backdoors into popular source code repositories. For example, an attacker might change a string literal check or a function call to make it always succeed or always fail. In an invisible manner by changing one of the strings characters to a homoglyph. Let's take a look at the example in the code snippet here. These two functions appear identical. However, the bottom function name uses the Cyrillic H character that you can see here, which counts as a completely different function name. A code later in the program may call any of these two functions in an indistinguishable manner, and the logic that will be executed will be different. Another invisible method that was introduced in the Trojan source paper was the Unicode bidirectional control characters. These characters are normally used to control the flow of text, either right to left or left to right for different languages. When using bidirectional control characters in source code, the Unicode encoding can produce strange artifacts such as source code line that visually appears in one way, but parsed by the compiler or the interpreter in another way. So for example, take a look at this code snippet in the left, which is the original code. From the reader's point of view, the code appears not to print "you are an admin" since is admin that you can see here is false. However, as can be seen in a snippet on the right, if a Unicode BD control character was inserted in the correct position in the condition check that you can see here, the check line could actually be interpreted by the compiler as a full comment. So the entire if condition can be bypassed and the logic will be changed. So now that we know the technical information of the infection phase, the payload phase, and the obfuscation techniques used in malicious packages, let's continue and talk about methods that we use for detecting malicious packages in real life. For example, in your development lifecycle in project that you developed. We will present several practical techniques for this purpose, for the detection of both known and unknown malicious packages. Let's start with detecting known malicious packages. If we take PyPI or NPM, for example, these repositories define processes in which users can report on malicious packages. You can see here in the screenshot a package that is tagged as a security holding package. Because it was accepted as a malicious package and replaced with an empty project since it was accepted as a malicious package. When we want to check for known malicious packages, the most efficient way to do it is by query those repositories. As we want to get a complete picture of malicious packages in our project, we essentially need to do a few things. The first thing is to list our project dependencies and detect all of the installed third-party software versions in our project. The artifact of this project is called the Software Bill of Material, or SBOM, which includes all of the information on the installed third-party software, which we can use later to query those public repositories. This process might not be easy to perform in scale as part of your software development lifecycle. So it is recommended actually to automate the process by using a software composition analysis tool. So we, of course, can recommend you on our own solution for this purpose called JFrog X-Ray, which is not only a software composition analysis tool, but a complete solution for the management of vulnerabilities and software supply chain risks in your project, including the capability of detecting malicious packages. X-Ray scans the entire development pipeline from the code in Git to your IDE, through your CI/CD tools, and all the way down to the distribution to production. It essentially integrates the detection and prevention of malicious component in your development and build system. When we talk about detection of unknown malicious packages, we essentially need to find a way of identifying characteristics of malicious packages before they are known as malicious. So in JFrog, for example, we're not only updating X-Ray database with an up-to-date known malicious packages names and versions, but for the purpose of detecting unknown malicious packages, we also develop and run heuristic scanners that scan the code of software packages and detect anomalies in them. These scanners alert on possible unknown malicious components. This scanner infrastructure is actually the foundations for all of the malicious packages that we research, publish, and disclose. So with these scanners, we were able to find new malicious packages, and of course, giving you the examples of the malicious packages in this webinar. This list contains examples for scanners that we developed. The way that the scanners work is to look for new, the way that scanners work for new malicious component packages is by trying to find evidence of malicious activity in any of the attack phases we discussed today. It can be in the infection methods, in the payload phase, by looking for evidence of the type of payloads that we presented, and also on the hiding methods, the obfuscation techniques, and for any invisible character in the code, for example. So it is theoretically possible to develop a scanner for every phase of the attack. So think about this list as a list of demonstrations of heuristic techniques. This way you can think about more techniques if you are interested in hunting unknown malicious packages. So let's take a few examples of scanners. So for example, for the Typosquatting and the Masquerading detection, the scanners check for similarity between popular packages names and other unpopular packages. So if we see a very popular package name that has a match with unpopular package name that looks similar, then we alert on that and research that, and also update our database and let the world know then that this is a malicious package. For the dependency confusion detection, for another example, the scanners checks internal packages names of popular targets on remote public repositories. And then if we have a match, we can look into it and understand better if this is a malicious package or not. For the download and execute, for example, we making a automatic reverse engineer on the code of the packages to build an AST that will and we try to find a connection between a socket activity that downloads data from the internet. And we try to find if it goes into an execution function, for example, popen or system in Python or Node.js. So this is another great example that gave us a lot of malicious packages. Let's take one more example from the obfuscation techniques. You know what? Several short examples. We detect, for example, base 64 in decoding and evaluation, just like the example that we see in earlier. And also, we specifically managed to detect a PyArmor obfuscator because it created significant characteristics in the code that we could actually sign. And also for the invisible characters detector, the homoglyph and the bidirectional characters, those are very easy to detect because normally source code of a known or any software package should not contain this kind of Unicode characters. So it was very easy for us to create those scanners, and we encourage everyone who has this interest also to do it as well. So we are nearing the end of the webinar, but we will not end without discussing the best practices for secure development to allow you essentially deal with the malicious packages security threat. So the first recommendation, which is the most important and basic method to deal with the malicious packages, as we said, is to use software composition analysis tool as part of your SDLC, the software development lifecycle. You can use, of course, our tool, X-ray, or any other software composition analysis available. This is the most important step. The second recommendation is to define policies and automate actions as part of DevSecOps processes based on the results of the software composition analysis tool. The policies should break the build, actually, and send alerts when a malicious package is found. Unlike CVEs that we can find a lot of CVEs in our code and we should examine them, a malicious package is a very unique and very hard threat. So when we see a malicious package that was detected, we should treat it as a high chance of true positive. So we actually recommend to break the build in this case. The other thing we could recommend is that you configure your build system to exclude remote repositories for internal packages. This is for preventing, of course, dependency confusion attacks. Essentially, we want to better manage the way that external repositories are queried when resolving dependencies in the build process. For example, by setting up exclusion rules to prevent searches for internal private packages in remote repositories, or defining the order in which varied repositories are searched in order to resolve a dependency. More information is available in our blog post here in this URL. So I recommend you to read it. Another thing we recommend is to use strict versions for external dependencies. We want to avoid automatic fetching of a high version malicious package unless we perform a full DevSecOps tests on a new version of our software that we publish. So this will make sure nothing was broken in the update and everything is safe, so we can go to production in this case. Specifically in Node.js, for example, the default behavior of NPM is to add a caret sign to dependencies version numbers, which NPM treat as this version or any greater minor patch release. We can overcome that by editing the package JSON and remove any caret or tilde, so NPM will install the exact version that we want. So this is a very good practice when you don't release a new version of your software and you don't test it. We can also use a package lock JSON to lock the transitive dependencies to a specific version. This should be done with caution, because although we can promise that malicious updates won't be received automatically, also security patches won't be received. So it is recommended, again, to update dependencies when releasing new versions of your software and test them end to end. We also would like to encourage the usage of open source tools that you can see here. Those tools can help you deal with the malicious packages and prevent them from infecting your project. The first one is PyPI, which can detect name similarity to avoid the typosquatting attacks on your project. The next one is pproxy, which is an open source tool that we developed and published to the community. It is essentially a small proxy server for pip that modifies pip behavior, the same behavior that we talked about, to install external packages only if the package was not found on any internal repository. This fixes the dependency confusion issue in pip, which prefers the package that has the newer version, regardless of whatever it comes from. Lastly, we have a few more open source tools that we developed and published to the community for NPM packages security. In the link below, you will find the tool NPM Secure installed that can help you validate the versions lockdown of your dependencies list in NPM, and also a package checker that analyzes a node package and reports on a suspicious heuristic to help determine the safest package version to use in your project. The last tool is NPM Issues Statistics, a very interesting tool that analyzes projects to find unusual activity that might indicate a compromised dependency. Finally, if you have any question in the future, you can contact me by email. I would be very happy to answer on your questions on malicious packages and supply chain attacks. Of course, we have the Q&A session right now, but also in the future, and feel free to do that. And also feel free to visit us in research.jfrog.com, where you can find all of the malicious packages research projects that we talked about them today, as well as deep analysis of 0 days vulnerabilities found by JFrog security, and also technical analysis on notable CVEs that we research constantly.
Great, thank you so much, Jonathan. We have
Thank you, Rebecca.
Just
small credits for the presentation.
Wonderful.
Great. Yeah, thank you. So I would like to give a special thanks to several people who worked on the findings and the tools that I presented today. First is Shachar Menashe, which is a senior director and the manager of our security research group in JFrog Security. Also special thanks to Andrei Polkonicheko, who worked on the majority of research blogs and the projects that I presented today. I would like also to thank Ilya Hivrich, Omer Kaspi, and Michael Sverdlin, who played a key role in the research projects and in the development of the open source tools and scanners that we saw today. That's all. Thank you.
Great, we have some questions coming in.
Cool.
The first is, do you think this trend is tapering off or still continuing?
Well, judging by the amount of hits we get on our malicious package detection scanners, this trend is still continuing. We think in the future we might see more sophisticated attacks like Trojan packages with very well hidden code or even dynamic code, and also expansion of malicious activities into other repositories in other languages such as Java in Maven, Go, NuGet, and etc. So I think this is not the end for this threat.
Great. Our second question. Do you recommend version locking as a solution against hijacked packages?
Well, so as we said, we believe that upgrading packages is essential, of course, and recommend version locking only while migrating to a new version. So a DevOps pipeline should be put in place such that when a new package version for a dependency is released, the application complete test suite is run. And also DevSecOps measures are in place to conclude if the new version is vulnerable or malicious. If all tests pass, the new version should be used. If some tests fail, of course, the application author should make the necessary changes to migrate to the new version of the package. Upgrading is of course essential in order to get new features, improvement, and of course the most important thing, security fixes. So yes, with a note.
Excellent. Our last question that we got, what are some of the signs that a package is trustworthy?
Well, that's a great question, actually. I guess several things. I think that the first thing is high amount of downloads, stars and forks. You can check this out on GitHub or the Git repository of a project, or in the repositories of the specific language that you use, npm, PyPI. So the first thing is simply to check that it is popular enough. I think it's also important to check that it is maintained. Maybe the last commit is less than 1 month old. So the project, we can make sure the project is not abandoned. Also, it's of course important to check that the project does not have any open security vulnerabilities that were still not handled. It's a good practice also to check for obfuscation, I guess, because obfuscation usually is an indicator for malicious activity. And another thing, for a specific version of your software that you want to use, the latest version of the package, you have to check that it is not too new. I mean, like if it's not more than 2 or 3 days old, because normally when we see attacks by malicious actors to infect packages, they insert a new version and then the entire world is infected within a few hours or within a day from the attack. So it is important to check that you're not downloading a very new package because of this reason.
Excellent. Thank you so much, Jonathan, and thank you all for joining. We're so excited to have discussed the content with you today. We hope it was informative. And if you have any questions or would like to sign up for future webinars or workshops, please visit our website at jfrog.com. Thanks again. Have a great day.
Thank you.